We're gonna move right into our program with live talks. And first up is Carle Pieters from Brown University, who's graciously agreed to give an overview of the composition and environment at the South Pole of the Moon. Take it away, Carle.
Okay. Very good. I'm going to talk about the local composition and environment at the South Pole. Let's go to the next slide. We're all familiar with the near side and the far side of the moon from decades of study and exploration and the lunar samples that we have. But now we're going to a different kind of environment that none of us have any direct experience with, but is going to be setting the stage for our exploration in the decades to come. The South Pole. Next slide, please. There's a wonderful report, and I think Sam Lawrence will talk about many of the concepts that were highlighted in the science definition report. I highly recommend it. A lot of the discussion, of course, is on the anticipated volatiles that we'll find and the diversity of the environments that they'll be in. Today, I'm going to be emphasizing the local geologic composition and environment to set the stage. Others will be talking later about volatiles. Next slide, please. Okay, the first thing, of course, is that you've all seen this wonderful mosaic produced by the LROC cameras. It is a mosaic that is acquired over a full month of observations, probably several months to pick the best images. So it's not a single shot. You can't look at the character of the South Pole in a single image, but you can, excuse me, produce an image that, oops, okay. You can produce an image that includes the kind of environment that you're describing, and I'll talk a little bit about some of those conditions in a moment. Next slide, please. An important thing that is quite different from our previous experience on the surface of the moon, where we had a high sun, wonderful illumination of the terrain. In the exploration of the poles, the sun is always going to be on the horizon or below the horizon. That's why we get permanently shadowed areas. The solar disk is about 1/2 degree, and the moon rotates about 1/2 degree an hour. So over 24 hours, the position of the sun on the horizon will move about 12 degrees. And during, say, a 3-day or 3 Earth day stay on the surface, the position of the sun will have moved approximately 36 degrees along the horizon. But it will never get high in the sky. We only have the horizon illumination from the sun, and we have to plan carefully and accordingly. Next slide. Okay, let's look a little bit more detail about some of the surface. We're all familiar with the South Pole and Shackleton crater. I've picked an area, a little crater about 7 kilometers from the Shackleton rim that we're going to look at in more detail. Next slide, please. This is a crater that's 300 meters across. It's 7 kilometers from Shackleton, and it looks sort of like a crater. You know, you look at the surface here. This is one of the lovely NAC images that, of course, can enhance the illumination so you can see the details. And you can see some of the topography that's associated with the terrain around Shackleton, but you can see that it's dominated by craters. That's the principal kind of landform that occurs on the surface of the moon everywhere, including the poles. Let's go looking at this crater a little bit more closely, and it's why I chose this particular crater. The next slide, please. because this crater has some boulders around it. And it's the only place that we can see positive features rather than holes in the ground. And one of the things you can see quite readily, the little scale mark there is 50 meters. So this boulder that's a little bit to the left of center is about a 10-meter boulder, but it casts an enormous shadow, about, in this case, 6 or 7 times its size. So we know, and we've predicted, but this at least is a in situ measurement of what shadows at the poles look like for when you have positive features, not just holes in the ground. And the astronauts, all the equipment they take to the moon will have comparable shadows. Next slide, please. Okay, well, we're going to have deep shadows. We know that. That's using natural solar illumination. Well, let's examine the character of the pole in a different light. Next slide, please. Namely, we have the wonderful LRO in orbit that has a laser altimeter. It shoots laser beams to the surface, and by the timing of the return can map the topography. But it can also, and has beautifully, measured the amount of radiation that's reflected. And that gives us what we call albedo, it's an artificial illumination of the surface, but gives us very important information that's quite useful for understanding the character of the environment at the South Pole. Next, please. This is what it looks like. The black circle is the same area we were looking at in the deep shadows. This is now looking at the same surface at 1 micron, which is a little bit longer than visible wavelengths. But to a first order, it's what we would see if we could see at 1 micron the surface. And you can see there's craters, there's high albedo areas that are likely immature areas. Let's look at things, this kind of image in detail and what it can tell us about the character of the South Pole. Next slide, please. Okay, albedo is normally measured by the amount of reflected sunlight, and we're familiar with the full moon perspective that we all see once a month if there's no clouds and you have good binoculars or a telescope. Next slide, please. Lola uses the orbiting laser to receive reflected radiation, and it can measure the same geometry as what we see under full moon, namely can look at the surface without any shadows, but at, as I said, this 1 micron wavelength, which is a little bit longer than what the visible wavelengths that we're familiar with. Next slide, please. Here's a full moon image, similar to what we normally see with our eyes when we look at it. This, however, was obtained by the spacecraft using the laser altimeter. And to a first order, it looks not that different from what we're familiar with. Next slide. And we can identify some of the basic compositions. We can identify the very dark basaltic mare. They're low albedo because they have iron-bearing minerals in them, a lot of it. The feldspathic highlands have a high albedo. They have a very low abundance of iron-bearing minerals. Apollo 16 was in feldspathic highland terrain. And the third sort of albedo kind of feature you can readily see is freshly exposed materials, whether it's in the highlands or in the basaltic mare, is always brighter than the surrounding terrain and gradually decreases in the contrast with age. So to a first order, and even with this Lola image, we can identify basaltic dark mare and the feldspathic highland breccias quite readily, and immature areas. Next slide, please. Okay, so here we have, for those of you who are interested in obtaining or want more information, this was written up very nicely by Paul Lucy, and you can find it in JGR Planets, 2014. So here are the results for the Earth side and the far side in this low albedo. Next slide. Next, please. Okay. Because it's global, you can get the same kind of information for the northern hemisphere and the southern hemisphere. Well, of course, we're going to look at what's seen in the southern hemisphere. Next slide, please. Okay. Looking at the hemisphere as a whole, we can see the Apollo 16 area up near the limb. We can see Tycho, the same as our near side image, but we have a straight on image of what the South Pole terrain itself looks like. And you can see where I'm heading on this, namely that I discussed the composition of the basaltic terrain that we see readily, the highland feldspathic breccias that we're familiar with Apollo 16 and Luna 20. That kind of feldspathic terrain clearly extends across the South Pole. That's not to say there aren't other really interesting things near the South Pole, but for example, the low albedo material from South Pole Aiken is a couple 100 kilometers away, as is the nearest basaltic terrain. So basically, the terrain is feldspathic highland breccias. Next slide. This again, I should have, this is naming the names of what's around us. Okay, let's go to the next slide, please. You don't have to take my word for it that the high albedo terrain is feldspathic breccia. We have independent data measured by Lunar Prospector of the iron abundance, and it's a very nice, clear confirmation of what we were just talking about, namely that the basaltic mare have high iron minerals in them and always have a higher iron content, even though the spatial resolution measured by Prospector was low. The character of the terrain type that we see across this part of the moon, in particular the South Pole, is clearly feldspathic highland feldspathic terrain that has a low abundance of iron-bearing minerals. Okay, the next slide, please. Okay, here we have our now two familiar terrains for the South Pole, the sunlit side on the right and the laser lit side on the left. They're the same terrain. You can identify some of the same features, but the information, of course, that each provides is different, and both are quite valuable. Next slide, please. Okay, and I'm now gearing into some of the concluding remarks. The terrain around the South Pole is a continuation of feldspathic highlands with a low abundance of iron-bearing minerals. Now, although the details, of course, will vary and we will find surprises, the bulk mineralogy is expected to be very similar to that of Apollo 16 and Luna 20. We do expect some of the minor elements, say the rare earth elements, to be distinctly different, and we look forward to what we find. But the basic composition will be a feldspathic breccia. Now, and here's what is going to be important for the discussion today. Other compositions of enormous scientific value, namely any material from South Pole Aiken Basin, diverse basaltic materials, although 700 kilometers away, may be incorporated into the breccias that we find at the South Pole. Next slide. So The lunar South Pole is, and let's go to the next slide, almost entirely feldspathic breccia terrain. Okay, that's good. Next slide, please. However, rare exotic materials, say from South Pole Aitken, Tycho, Schrodinger, basaltic terrains more distant, have probably been incorporated into the local breccias and regolith, but they will be very difficult to find and identify. Next slide, please. But they could be identified. And here's the whole reason we're having this workshop. Capable tools to assess the site and collect key samples should certainly be developed and tested. Astronauts should be trained in both lunar geology and mineralogy and how to work with these tools in the kind of environment that's expected at the South Pole. Now, given the character of the polar terrain, the extreme low lighting conditions, the feldspathic breccias that are everywhere, let's not to mention the wonderful volatiles that we clearly are going to find and be looking for. But the use of modern tools is essential to carry out scientific exploration. Next slide. And this is my last slide. Let me just leave this concept because this is the most important thing that's going to be discussed in the next several hours. Given this unusual character of the terrain that we have not yet any experience with, we'll get some from the VIPer mission and other landers near the poles. So hopefully we will not go into it completely blind, so to speak. But the use of modern tools is absolutely essential to carry out scientific exploration activities. Thank you.
Thanks very much, Carly. That was a fantastic overview. Really appreciate that.